In this video, we're going to look at Chapter 23, Elimination Reactions, as well as just a few small notes on structural isomers of functional groups. Elimination reactions are reactions in which a small molecule is removed from a bigger molecule, leaving a double bond in the larger molecule. We have seen an example of this before in the preparation of ethene gas. This was where we passed ethanol over aluminium oxide and produced ethene gas and some water. If we look at the bonds broken here, we can see that there was a bond broken on each carbon in the ethanol. First of all, we have the carbon to hydrogen bond broken, and then we have the carbon oxygen bond broken here. This leaves us with 2 hydrogens on each carbon atom. In order to satisfy the octet rule and to fill the bonds it needs to, carbon must have 4 bonds. So what it's going to do is form a double bond between the 2 carbons where bonds were broken. We've also got a bond forming between hydrogen and oxygen here to form water. Notice how the double bond forms between the 2 carbon atoms which have had bonds broken in order to complete the 4 bonds that carbon must have. Another example of this can be when we have a secondary alcohol. So here the OH group is on the central carbon. This is actually the only elimination reaction that's on the syllabus. However, there is one other one that seems to come up every now and then. So here we are going to see bonds broken on 2 carbons. Now it doesn't matter which one you choose, there's 2 correct answers for this in order to draw it out, but the answer, if you were to name it, would be the same either way. So you're going to break the bond between carbon and oxygen and then one of these carbon-hydrogen bonds. And what we'll see happening is that we will get a double bond forming between the carbon. So in this case, we're breaking that bond. A double bond forming between the 2 carbons which have had bonds broken. And we have the formation of H2O here. We also saw in the addition reactions, we saw the addition of molecules to alkenes, where we add a molecule across a double bond. An elimination reaction is the reverse of this, and so it does sometimes come up in questions about the removal of this molecule and recreating that double bond again. This is going to be in the complete opposite way of the addition reaction, but in the same way as we saw the elimination of water from alcohols. We will break 1 bond on each carbon to remove our HCl, and in order to satisfy the octet rule, carbons will form a double bond in between them, and we'll also get the formation of a bond between H and Cl to produce our hydrogen chloride. Another question that can come up, not that often, but it does come up, is about structural isomers of functional groups. So these 2 molecules here are structural isomers of each other. You might want to use this as a time for revision and pause here and try to name them yourselves. If you've that done, we're going to carry on. So on the left, we have a ketone, and on the right we have an aldehyde. And if you were to count up the number of atoms in each of these, they have the same molecular formula, C3H6O. That means they are structural isomers of each other. Their names are propanone and propanal. So in any situation, if you were given a ketone, the corresponding aldehyde will be a structural isomer of it. For example, if you were given butanone, butanal would be a structural isomer of it. If you were to take pentanal, an aldehyde, then pentanone, the corresponding ketone, would be a structural isomer of that. Again, structural isomers here, if you want to pause and use this as revision and try to name these two substances. The one on the left is a carboxylic acid and the one on the right is an ester. Again, if we count up the number of each type of atom in each molecule, they will have the same molecular formula, C3H6O2. And as you might guess from what we went through previously, these are both structural isomers of each other, propanoic acid and methyl ethanoate here. Now, it's not as straightforward in that they don't have the same root of the name as the last example did, but if you were given propanoic acid, you count up how many carbons are in there. There's 3. They're represented in black up there in propanoic acid. And if you draw out an ester with 3 carbons in it and all your bonds, your structural bonds are all in place, and you have the functional group drawn correctly, then they will be structural isomers of each other. Here's a question. I'd recommend pausing here and seeing if you can answer the questions yourself. So for reaction A, identify the type of reaction. So we are going from an alkane to a chloroalkane. This type of reaction is a substitution reaction. That's our free radical mechanism. The reactants required for that would, in part 2 of the question, would be the ethane that we have here, chlorine, Cl2, and it's important to mention here that you would need UV light in order to activate this reaction. For reaction B, we are going from ethene to ethane. So this is an addition reaction, and the reactants you're going to require here are your ethene and H2, hydrogen gas, and that's going to be added across the double bond. Finally, reaction C is ethene to chloroethane. So reaction C is also an addition reaction, and you're adding HCl across that double bond. So your reactants required there are going to be the ethene that we see here, and HCl, hydrogen chloride. Then in part 3, it asks us to write the mechanism for A. So this is your free radical mechanism for the addition of chlorine to your alkane. The steps are outlined here. So we have initiation, that's an I, propagation part 1, propagation part 2, and then our 3 options for termination are all here. So it's worth maybe trying to do that yourself, as I mentioned before, or just going through and seeing if that makes sense to you here as it's written out.